In this vector series, we're going to develop a technique that is very useful to solve complicated vector identities. And the whole technique really hinges upon this particular identity here, that here on this side of the equation we have the epsilon permutation symbol, and then on this side of the equation we have the Kronecker delta symbol. And it looks like a rather formidable identity, but we will prove it in future videos, and we want to understand it thoroughly because it is a very, very powerful tool for proving much more complicated vector identity problems. And some of the vector identities that we'll encounter in the future videos will have this. We'll prove this one. Here's another one that we'll look at. Here will be another vector identity that we will prove, and we will also have these included amongst our repertoire. And again, the whole method hinges upon this identity. So we're going to lay the groundwork to prove this identity. Then once that's done, we can use it for solving very complicated vector identity problems. Now, in this video, we just want to work a little bit with the Kronecker delta symbol for just really an elementary application, and also show some of the basic properties of it. But to get us started, let's suppose that we have a vector x that we will write out in component form like this, just in three-dimensional space. So it looks something like this. Where E1, E2, E3, they are unit vectors. They are also orthogonal to each other. Now, another more shorthand way of writing vector x out in its component form would be to use a summation sign, say xi ei, and then we're summed over from I equal 1 to 3. So here we have I equals 1 to give us this term, then I equals 2 to give us that term, plus I equals 3 to give us this term. Or notice here that I appears twice. It is a repeated index, and the convention is to save yourself writing, when you see a repeated index, that automatically means then that you're summing over that index. So we could say that x, the vector x, equals xi ei. And again, this repeated index means automatically means you're summing over it, and in our videos we are summing over from I equal 1, I equal 2, I equal 3, unless we state different. Let's suppose that we have another vector, say y, and we'll express it in component form the long way. Say we have yj ej, or of course we could express it like this. What happens, we want to consider what happens when we take the dot product of vector x and vector y. Before we do that, let's take a look again at these unit vectors. We said that they are orthogonal, and they have unit length of 1. So if we take the dot product, it's either going to equal 0 or 1. If we have different numbers here, it's going to be 0. For example, if we have E1 dot E3, they're orthogonal, so of course that is 0. But if the numbers are matching, so we have E2 dot E2, then of course that's going to equal 1. So this equals 0 if I does not equal j, and it equals 1 when I equals j. Now another way of expressing this is, instead of writing it out like this, we could say this equals the Kronecker delta symbol ij. This is simply an abbreviated way of telling us that this equals 1 when I and j are the same number. If they don't match each other, if we have different numbers here, then it's 0. So Kronecker 3, 3, that's 1. But if I have 3, say 1, then that's 0. They have to be matching to give us a value of 1. If they're not matching, then it's 0. So now let's consider taking the dot product of our vector x and our vector y. And we'll write them out in component form. So we have x dot y, and we'll use our summation signs here for this problem. So we have summed over I of xi ei, then we're going to take the dot product of this summation summed over j of yj ej. So we've just written our two vectors out in component form. Something that we want to be familiar with concerning operations with our sigma addition operation here. Suppose that we have this expression multiplying this by this. Let's do that then. Keep this the same, and we'll sum over I from 1, 2, and 3. So here it is, times this. And then here we're going to sum over j from 1, 2, and 3. So it gives us this. So multiplying this times this gives us this expression times y1 plus this expression times y2 plus this expression times y3. Now, what happens if we do our multiplication, but we have it inside a single summation sign, but here we're summing over a double index, I and j? Will this give us the same, is this the same as that? So let's see. We have this under the same summation sign, summed over I and j. So let's ignore j for the moment and just sum over I. That will give us x1 plus x2 plus x3 times yj. And now j goes from 1 to 3. So that gives us, here's j1, there's j2, there's j3, which is exactly what we had on the previous page. So multiplications like this can also be considered under a single summation sign over a double index. And that's what we can do right here for this problem. Remember, when you're taking dot products, the scalars are distributive, so you can say it's just the sum over I, j, xi, yj. Then we have ei dot ej. And now it's under a single summation sign, but we're summing over a double index. But ei dot ej, that's the same thing as that gives us just our Kronecker delta symbol. So let's write this in place of EI dot EJ. And now what does this mean? Well, this is going to be 0 unless I equals j. So this now becomes this expression. Summed over I, xi, yi. This is 0 unless j equals I, then it's just 1. So now we have this expression, and this equals x1, y1, summing over I now, plus x2, y2, plus x3, y3, and that's equal to x dot y. So it's telling us our dot product is this in component form, which of course we knew all along, but you may not have approached the problem from the standpoint of using the Kronecker delta operation. So that's what I want to do in this video, is just give a simple demonstration of an example of using the Kronecker delta product. So let's just consider the Kronecker delta product a little bit more. We know that we can write a vector in general form like this, say x, I, EI, and of course writing it out in component form is just x1, E1, like this. And a dot product can be written like this in component form. We just established that. Now what happens if we have, say, x, take the dot product of our vector x with one of the unit vectors, say EI? Well, we know that if we have the vector x and we take the dot product, say, with E2, that just gives us x2. The dot product of vector x with that unit vector is just the component of the vector x along that unit vector. But let's think of it in a more general sense. Vector x we could write like this, say x, j, ej, and then we'll take the dot product of this with EI. Now here we're going to get the Kronecker delta symbol equals xj delta ij. This could be written delta ji or delta ij, doesn't matter. It's going to be the same thing. But this is 0 unless j equals I, then it's 1. So this equals xi. So we've just shown here then that taking the dot product of x with a particular unit vector indeed gives us the component vector x along that particular unit vector, but we did it now using the Kronecker delta approach. And let's just examine some more basic properties of the Kronecker delta symbol with a few simple examples. In the future videos, sometimes you will see this expression, say delta k, delta k. Well, here we have a repeated index, so that means we should be summing over it. So let's sum over this one first, and for the moment ignore that one. So that will equal delta 1k plus delta 2k plus delta 3k. And now this k can be 1, 2, and 3. This can be 1, 2, and 3. And this can be 1, 2, and 3. So this will equal, starting with this one, k equals 1. We have delta 1, 1. Now, k can be 2, and it can also be 3. But of course, these are going to be 0, because here we have delta 1, 2, delta 1, 3. They don't match, so these are 0. The only time we get a non-zero expression with delta is when the indexes are the same, and of course it's just equal to 1. So these are 0, and the same thing, of course, is going to happen with these. K can be 1, 2, and 3, or when k equals 2, we have that. When it's 1 or 3, then we have delta 1, 3, delta 2, 3, or delta 2, 1 when k equals 1, but these are 0. And then for here, k can be 1, 2, and 3, but the only non-zero term we get is when k is equal to 3. So, and this of course is 1, this is 1, and this is 1. So, delta k equals 3. And we will encounter this expression in future videos. Suppose we have this, delta ij times delta jk. When you encounter this, you can just contract the k's out, or contract the j's out, the repeated one. Why you can do that in this instance, we can just look at it. You can say, well, this is 0 unless j is the same as I. And this is 0 unless k is the same as j. But j has to be I. So we're saying k has to be equal to I, or this whole left side is 0. Again, j has to be I, therefore k must also be I, because k has to be the same as j is. So we're saying this is 0 unless k equals I, and that's what that tells us. So in future videos, when we count this type of expression, then we just take these out, and it's equal to that expression. Now, suppose we have it like this, though. Delta ij, and then delta j, not a different letter, but I. So now we have two repeated indexes. So here, let's sum over the I and ignore j for a moment. So you have delta 1j, delta j1, then I equals 2, so we have delta 2j, delta j2, then j equals 3, so delta 3j, delta j3. And now j can be 1, 2, and 3, j is 1, 2, and 3, j is 1, 2, and 3. But the only time this is non-zero is when the number for j matches this one. So j can be 1. So we have this. Then when j is 2 or 3, those are just going to be 0. And the same thing happens here. J can be 1, 2, or 3, but the only time we get non-zero expressions is when j is 2. And same thing here. This would be delta 3, 3, delta 3, 3. When j equals 1, we get this. If j is 2, non-matching index, no contribution, when j is 3, it's a non-matching index, no contribution. Same thing here, j can be 1, but the numbers don't match, so it's 0. J can be 3, but the numbers don't match, so it's 0, only when j equals 2 do the numbers match. And same thing here. And of course, this is 1. This is 1. This is 1. So this kind of an expression, delta ij delta ji equals 3. And again, we'll make use of these expressions in future videos when we consider more properties of the Kronecker delta symbol, and we try to use it in more complicated situations that we've done in this video. Anyway, this is the first video in our series then on the super vector identity technique. The playlist for it, along with all the other playlists, will be featured here at the website digital-university.org.